As Kathy said, I'm a physicist. I'm not with Extension, as I mentioned earlier, but I was born in rural South Dakota, and I'm very much a product of land-grant institutions. In our last presentation, I was very pleased to see South Dakota State University, one of my alma maters, on the screen. I also studied at Texas A&M and did my graduate work at Utah State University, all of which land-grant schools, and have long felt that Extension is built for this topic of climate change. And I'm very pleased to have this conference going and to be here speaking to you and to have you here. So thank you very much. I would also like to say something I always say to audiences when I'm talking about climate change. When the topic is climate change, you are confused, you have every right to be. And you're not alone. The volume of confusing and conflicting information out there is just extraordinary. That said, as a society, we simply can no longer afford to be confused about this topic. And so I think that's very much what this workshop is about, and the work in Extension moving forward is to clear away some of that noise and get ourselves working from a common base of understanding from which we can then understand how to move forward. If we're going to summarize the topic of this workshop moving forward, I think we can do it with one word, and that is change. And as you've seen, there is a great deal of change going on in climate change, certainly in the physical environment, but it's not limited to just the physical climate system. There's a lot of change happening in Earth's living system, the biosphere, of course, and a great deal of change happening within what I sometimes call the anthroposphere, the human systems, technological, economic, sociological. And so also, as you've seen and heard, there's a great deal of effort at the moment going on to adjust to the changes that have been happening. And much of the rest of this workshop is dedicated to talking about how do we go forward and adapt. But it's important that we keep in mind that this notion of adaptation is not a magic wand that you can wave. Some adaptations will be straightforward, some will be very difficult, some will not be possible. And so it's good to keep in mind, I think, in fact, critical to keep in mind, that the very easiest adaptation to make is the one that you don't have to make. And that brings us to the notion then of lessening the change that happens. And so mitigation very much has to be a part of the conversation, and certainly part of our knowledge base going forward, and you going forward as you're going to talk to your clientele and your communities. So these notions of adaptation and change often get mixed, and I've been asked to maybe speak to that a little bit. And I'm going to speak mostly to this notion of mitigation and how it is connected to adaptation. So first of all, you've heard about change. Let's look at it. This is the warming of the planet since the late end of the 19th century through the middle of the 20th century to today. And we can see that the entire planet is warming, and that this warming is not evenly distributed. But if you average it, as we've already heard, we've warmed about 1 degree Celsius over the last century, most of that in the last half century. And to put that in context, that's a warming rate of about 20 times faster than the rate that the Earth warmed coming out of the last ice age. So from an Earth system standpoint, this is quite a large change, and it's happening very quickly. And as you've already heard, there are impacts happening to which we are having to adapt and to adjust. Some of them, with this level of warming, have already been catastrophic to some people in some places on this planet. But of course, this is the change that's in the rearview mirror, and what we need to look at now is the change coming. And we've had a talk, a very nice summary by Greg about modeling coming in. So I want to just frame this in maybe some ridiculous little cartoons here. The first one is a thermometer. And based on the modeling that we've heard about, so on the left-hand side, graduated in Fahrenheit, you're welcome, 45 degrees, the global average temperature of the planet at the depth of the last ice age. The green oval is the climate in which humans, and most importantly the human ecosystem, evolved and in which we have always existed. The region between the two lines up there is known as the Holocene. This is the climate in which human civilization evolved, to which we are highly adapted. And the purple oval is the range of projections moving forward in the coming decades through the end of this century for a change in global average temperature. And this is all to scale. And I think it's you can see there that that's quite a spread, but that no part of that purple overlaps the green. We are moving to an entirely new climate, one in which we have never existed. And I think you should let that sink in for just a moment. The lower third or so of that purple oval pertains to these low carbon emission scenarios that were talked about earlier. The upper 2/3 pertain to the high carbon emission scenarios. And this change moving forward in that purple oval brings with it some pretty extraordinary risks for humans and human civilization and the human ecosystem. To try to maybe get a better sense of that, let's take it down to some regional examples. First, we'll start with temperature. These are summertime temperature changes over North America. And the spread we have is something on the order of 4 degrees or so Fahrenheit for most of the lower 48, including the Southwest. An additional 2, as you've already heard, an additional up to the term 8 degrees was used earlier. That's for a seasonal average or a year-long average in summertime, up to maybe 11 to 12 degrees Fahrenheit by the end of this century under a high carbon emission scenario. Something else we're also interested in that has also been mentioned is snowpack. There we go, sorry. Oh, by the way, the dark red in the Arctic there is up to a 25 degree Fahrenheit rise in temperatures in the sun. So these are really quite extreme changes that are about to play out potentially over the next several decades. Spring snowpack is very important to us in Utah, where I live, and I apologize, I don't have the data for the Cascades on here, but this simulation, this is both data and a simulation. We're going to look at the snowpack, the springtime snowpack over the Rockies here. I'll just point out that the blue is the deeper snowpack and the white is thinner. And we'll first look at some observations, some actual data going back 50 or 60 years or so, and then we'll transition to some projections for this snowpack moving forward in the coming decades. So we see that certainly there is some variability in snowpack. Some years are snowier than others. We all know that. As you move past 1980, that variability actually increases. And as we move into projections, you see moving towards the middle of this century, a steady decline in springtime snowpack. And then as we move into the latter half of this century, the springtime snowpack essentially disappears. This is very important for us in Utah. Most Utahns get most of our water from melting snow. This is under a high carbon scenario, so it's combining temperature and precipitation projections, and as been mentioned, not surprisingly, more of the precipitation then falls as rain rather than snow. One more projection I want to show you is with soil moisture. This combines temperature and precipitation projections. And of course, you can find yourself in a somewhat perverse scenario where you get moderately more precipitation, but the soil ends up drier, and that's because evaporation intensifies dramatically as temperatures go up. So this first simulation shows us soil moisture drying through the middle of the century under a moderate emission scenario, and then somewhat stabilizing in the latter half of the century as we ostensibly move to lower carbon emissions. But still, this is quite significant drying across most of the United States. Now we'll look at a high emission scenario, the one we're on. Steady drying through the middle of the century, dramatically intensified through the end of the century. And that, again, is the current path that we're on. I'll simply tell you that the people who studied these results will refer to the low carbon scenario on the left as dangerous, and the high carbon scenario on the right is catastrophic. And that term is used sort of technically, meaning essentially unadaptable. One more projection I want to show you, done by the same group who did the previous one, is looking at the risk of megadrought this century. This study just came out in the last couple of months. And megadrought being defined as an extended period of extreme aridity, 35 years or longer, exceeding the dryness of the worst droughts that we saw in the 20th century. This particular map shows the risk of megadrought this century for a 2 degrees Celsius rise in global average temperature. The dark areas are very high probability, 95% or greater. The lighter colored areas, lower probability, say 15%. And then this changes as the temperature scenario changes. Temperature change of 4 degrees Celsius, temperature change, global average, of 6 degrees Celsius, which we are on track for this century in the high emission scenario projections. It's good to have a little humor, but the point is this is the mainstream level of scientific understanding of what is happening to us and the risks that we are facing as we move forward. To try to get a sense of, to try to get a sense of that risk, I'm just going to put up a couple of quotes. First, from Lonnie Thompson, quite a distinguished glaciologist. Virtually all climatologists now convinced global warming poses a clear and present danger to civilization. Kevin Anderson, quite a prominent carbon modeler in the United Kingdom. A 4-degree future is incompatible with an organized global community. By that, he means global average temperature rises of 4 degrees Celsius or more. Likely to go beyond adaptation, devastating to the majority of ecosystems, and a high probability of not being stable. Now, you've gotten a lot of information so far this afternoon. It's been very good information, but it seems kind of clinical. And I just, again, want to say, these are completely pedestrian quotes. I can find scores and scores of such quotes from the scientists who do this work, not only in the popular press, but also in the scientific literature, which is becoming quite extraordinary. And it's not just scientists. People who do social systems, and in this case, defense, Brigadier General Stephen Cheney, notes the additional knock-on risks that we face could lead to humanitarian crisis of epic proportions. We're already seeing a migration of large numbers of people around the world because of food scarcity, water insecurity, extreme weather. And this is set to become the new normal. And so this leads us to the notion that if you take these seriously, and our state of knowledge gives us every reason to take this seriously, we need to talk about mitigation very seriously. And we are, as a global community, now talking about that very seriously. Last year in Paris, nearly 200 nations agreed that we need to mitigate this risk. And the goal that was stated is to prevent dangerous human-caused climate disruption of the system. Translating this into the physics, the idea is we want to limit the global average warming to no more than 2 degrees Celsius above pre-industrial temperatures. It would be better to only go to 1.5 degrees Celsius, recognizing that we've already warmed a little more than 1 degree Celsius. From a risk management standpoint, the equation becomes pretty simple. More carbon is more risk. We can identify a danger line, and given that danger line, physics can calculate quite straightforwardly a carbon budget. How much more carbon can we dump in the atmosphere and maintain a reasonable chance of not passing the danger line? So as we go forward, I'm going to use that 2-degree danger line, but let's recognize that really it's been redefined as closer to 1.5 degrees. So here's that carbon budget, about 1,000 units, calculated by a very large modeling study back in 2010, 1,000 gigatons of carbon dioxide. But that was 6 years ago, so we've chewed through some of that budget. And here's how fast we're going to chew through the rest of that budget on our present patterns of consumption. About 2 decades. So what the science is telling us very, very clearly is that dangerous climate disruption is underway. Catastrophic climate disruption this century is likely at this point, absent meaningful response. And we've got about 2 decades of elbow room to try to get a handle on that. That's just the physics. That's just what we're here. That's what we know from our understanding of the science. Here's that budget relative to our proven reserves of carbon. This is coal, oil, and natural gas that we have already found and are already extracting. And if we are to include the reserves for which we are using fracking and tar sands extractions, which we should, since we are, the physics is telling us really our budget is only about 1/8 of the reserves that we're currently exploiting. So the question then, of course, is how do you mitigate? How do we do that? What is the path forward? There are frameworks for this. And to summarize very briefly, the idea is we produce carbon by producing energy. We do it by producing food. We do it by producing pretty much everything, our stuff. And so moving forward to mitigate, we have to address these systems that do this. It means redesigning our energy system away from fossil fuels to much more low carbon, renewable, probably more distributed systems, probably involving some kind of carbon pricing. We need to redesign a food system, particularly look at soil practices, forestry practices, and livestock, which are contributing significantly to the greenhouse gas problem. And we need to redesign the way we approach economy, consumption, our views of lifestyle, and the mindset with which we move forward. Now, if this looks like a pretty big task, then you're seeing it about the way that I'm seeing it. Well, what I would say here is simply that the extensions clientele, AKA our communities, are clearly seminal in moving us forward in meaningfully taking the steps that we need to do if we are going to mitigate the risks that we are facing. And Extension is perfectly poised at this point, for the reasons that have already been very well articulated, to play a critical role in energizing and assisting this transition among your clientele. And I think it's important to note that this is not simply about deprivation and hardship. This is really very much about achievement. We need to transform an energy system which, even if it weren't contributing to a catastrophic change in our climate system, is itself hugely polluting and wholly unsustainable. We need to transform an agricultural system that is itself already not sustainable and hugely polluting, and we need to transform an economic system that is not sustainable and hugely polluting. And so there's a lot of upside to this, and the slide that showed up earlier, there's a lot of benefit to meeting these risks from a climate change perspective, but beyond that as well. So clearly, lots of change to happen, not just in our climate system, but within our society as well. Mitigation means a fair amount of change, and not just technical change, but social change. Doing this is making these social changes also will need to be adapted to. And so a part of adapting to climate change is adapting to the mitigation to climate change. And we need to do that for help our communities as well. And I think that Extension is very much the right organization to speed that along. So thank you very much for your attention.